finding a feasible vertex of the constraint polyhedron and the corresponding tableau is in general not an easy task. In this video, we see how to formulate this problem as a linear optimization problem, and then how to use the simplex algorithm to solve it. So here the simplex algorithm will be used to find a feasible solution, not an optimal solution. We consider here the problem in standard form, and like in the previous video, we will assume that the vector b is non-negative. But there is a major difference here. Because all the constraints are equality constraints, it's always possible to make sure that the vector b is non-negative. Indeed, for all the entries that may be negative, you just multiply the associate equality by -1, and it's still valid. So this is really a general case. Any linear optimization problem can be written in standard form with the vector b which is non-negative. We have n variables and m equality constraints. If you remember from the previous video, we managed to find easily the first tableau by selecting the slack variables as basic variables. Why? Because these slack variables have been added in the problem specification, and the associated column of the constraint matrix is the identity matrix. And because the basic matrix is the identity matrix, b-1 is trivial to calculate. Well, here we have no slack variables. But in order to use the same type of idea, we will introduce new variables using the same format that will enter the basis, such that the basic matrix is also the identity. These variables are purely artificial. We will call them auxiliary variables. And because we add them to the problem, at some point we'll have to get rid of them. And this is what we will try to do. So starting from this problem, I will add new variables that I will call auxiliary variable, and I will add one of them per equality constraint. So there will be m of them. Now the idea is that I will include them here in the constraint using the identity matrix as coefficient. Why? Because the idea is that I would like to say them as basic variables so that it's easy to calculate b-1. X would be non-negative as before, and xa would also be non-negative. Now, this is convenient to find an initial tableau. But what does it have to do with our original problem? Two comments here. First, what we are trying to do is to find a feasible solution, the initial feasible solution. So actually, in this context, we don't care of the objective function here. This is something that we will deal with later on. Right now, we focus on finding an initial feasible solution. The second comment is that in order to make the calculation of the first tableau easy, we have introduced these auxiliary variable xa, but we want to get rid of them at some point. And in order to get rid of them, we will try to make them as small as possible. Why? Because they are non-negative, so the smallest possible value is 0. If we're able to set them to 0, they will disappear from the problem. And this is what we will do. We will replace this original objective function by another one that says get rid of the auxiliary variable. Mathematically speaking, we'll have an objective function that will not involve the original variable, and it involves only the auxiliary variable. So this notation here is a vector of all 1, so this is equal to the sum for I equals 1 to m of x I a. So I call this the auxiliary problem. It's a problem that has been constructed from the data of the first problem, where we have forgotten the objective function, and we have included this new set of variables, the auxiliary variable. The objective function of this new problem consists in trying to make these auxiliary variables as small as possible, and hopefully to get them to 0. So this is my auxiliary problem that I call problem A. This minimizes the sum of the auxiliary variable, subject to ax plus I xa equals b. I put explicitly I here to show that it is the identity matrix. X and xa are non-negative, and the vector b is non-negative either. Okay, so now let's assume that x0 is a feasible solution for the original problem P. In that case, x0 verifies the two set of constraints, ax0 equal b, and x0 non-negative. It means that for the problem A here, the auxiliary problem, the solution that consists in setting x to x0 and x a to 0 is actually a feasible solution. Indeed, these two vectors are non-negative, so these two constraints are verified. And because xa is equal to 0 and ax0 is equal to b, this is also verified. So x equals x0 and xa equals 0, this is feasible for A. But look at the objective function of problem A. It's the sum of the values of the auxiliary variable. Here we have found a feasible solution such that the sum of the values of the auxiliary variable, therefore the objective function, is equal to 0. And because all the auxiliary variable must be non-negative, well, there is no way to do better than that. So it means that this solution is actually optimal. In summary, for each x0 which is feasible for P, we can create an optimal solution for the auxiliary problem by setting all the auxiliary variable to 0. In other words, if there exists a feasible solution for P, then there is a way to solve the auxiliary problem such that the objective function at the optimal solution is equal to 0. Now let's look at the contrapositive of this statement. If the objective function of the optimal solution of the auxiliary problem happens to be strictly positive, then it means that there is no x0 which is feasible for P. Great, so it means that the solution of this auxiliary problem will tell us a very useful information about feasible solution of the original problem. If we solve problem A and find an optimal solution such that the auxiliary variables are 0, well, the values of x will give us a feasible solution for the original problem. After we have solved problem A, if some of the auxiliary variables happens to be strictly positive, then we can conclude that the original problem has no feasible solution. It's an incompatible problem. And then we can stop. There is no need to solve it. There is absolutely no values of x that verify all the constraints. Now we need to solve this problem, problem A, and to do so we will use the simplex algorithm. The whole idea is that it will be easy to find an initial tableau to solve it. So let's see what the initial tableau is. Well, as we did in the previous video, we will put the variables that we have added xa in the basis. It means that the matrix B will be equal to the identity matrix. It means also that the vector CB, well, let's put it transpose, well, this is the coefficients of the basic variable in the objective function. This is the objective function. Actually, each of the auxiliary variable, that is each of the basic variable, enters the objective function with coefficient 1. So here this will be a vector which has only ones. Thanks to this, we can simplify the tableau. The top left part, because b minus 1 is the identity, is simply the matrix A. The top right is the vector B for the same reason. Now let's look at the reduced cost. We need to calculate the reduced cost for the basic variables, so the auxiliary variables. Well, we know this is 0. The reduced cost for every basic variable is equal to 0. And now we need to calculate the reduced cost for the non-basic variable. Well, in this case, the cost coefficient is 0 because there is no original variable in the objective function. So C here will be 0 for the non-basic variable. So we are left with minus 1 transpose times A. And finally, the last cell will be minus 1 transpose times B. As we have seen before, when you calculate the inner product between a vector of 1 and another vector, this is exactly the sum of all the elements of the vector, which is easy to calculate. Therefore, we see that the initial tableau for the auxiliary problem is easy to obtain. We copy the matrix A in the top left, we copy the vector B in the top right. For the reduced cost, we put all the reduced cost for the auxiliary variable to 0 because they are in the basis. And the reduced cost for the non-basic variable, so for the variable from the original problems, it's equal to minus 1 transpose A. So it's basically the sum of all the entries of A corresponding to each column, change the sign. Similarly for the last part here. This is great. We are able to easily calculate the initial tableau of the auxiliary problem. It means that we can apply the simplex algorithm and find the optimal tableau of the auxiliary problem. Now, two things can happen. Either the optimal value is strictly positive. In that case, we have a proof that the original problem has no feasible solution. We can stop here. Or the optimal value is 0. In that case, we have found a feasible vertex of the original problem. Actually, we can even recycle the last tableau to solve the original problem. To do so, we need to clean a little bit the tableau before we can start solving the original problem. Let's summarize the procedure to clean the tableau. So we consider the optimal tableau of the auxiliary problem. We know that all auxiliary variables are equal to 0. Indeed, if it was not the case, we would have already stopped claiming that the original problem was not feasible. But some of them may be in the basis. In that case, you need to pivot them out. You need to find a non-basic variable from the original problem and pivot these two variables. Get the auxiliary variable out of the basis and the original variable in the basis. Because the auxiliary variable is in the basis and is equal to 0, we are in the presence of a degenerate solution. So it means that this pivoting will change the basic representation, but the vertex of the polyhedron will be exactly the same. Actually, sometimes it's not possible to get rid of all the auxiliary variables. This will not be covered in the video. I refer you to the book and to the exercises in the MOOC to look at this specific case. When all the auxiliary variables are out of the basis, then you simply remove the corresponding columns. And before you can solve the original problem P, the last row of the tableau must be recalculated. Indeed, for the auxiliary problem, the objective function of the original problem has been completely forgotten. So now we need to erase the last row, which has nothing to do with the original problem, and recalculate the reduced cost and the value of the objective function of the original problem. And now we have a complete algorithm to solve a linear optimization problem. Let's summarize the procedure. The first thing you have to do is to write the original problem in standard form in a way that B is non-negative. Then you consider the auxiliary problem by including these auxiliary variables, one per constraint. And you can solve this auxiliary problem using the simplex algorithm because it's easy to find an initial tableau. If at least one of the auxiliary variables is not 0 at the optimal solution, we can stop and claim that problem P is infeasible. Otherwise, the solution X star of the auxiliary problem is a feasible solution of the original problem. We need to clean the tableau, including the calculation of the last row, and then we use it as an initial tableau to solve the original problem with the simplex algorithm. And then we know that this last step has two possible outcomes. Either it converges to an optimal solution because all reduced costs are non-negative, or it declares the problem unbounded because it has found a direction that can be followed all the way to infinity. In this video, we have seen that it is possible to find an initial feasible solution by solving an auxiliary optimization problem. It's easy to find an initial tableau for this auxiliary optimization problem. And after we have solved it, it gives us either a feasible solution for the original problem or a certificate of infeasibility. After cleaning the optimal tableau of the auxiliary problem, we obtain an initial tableau for the original problem. And therefore, we have all the ingredients for a complete algorithm that solves any type of linear optimization problem. three possible outcomes of this algorithm. One, we declare the problem as infeasible after having solved the auxiliary problem. Two, we declare the problem unbounded because during the second phase, we find a direction that we can follow all the way to infinity. Or we have found an optimal solution.